All right, welcome back. Let's do the exercise at the end of the section. We'll start with 2.1.1. What are the conclusion and the assumptions of the following argument? Well, let's look at this. We say theorem and proof. So proof is going to prove something that came before it. I think it's going to be in the theorem. The theorem has a let here. Remember, that was a clue word to say assumption, so this one can't be it. The then is going to be the clue word, I think, to say that this is a conclusion here. So I'm going to make the assumptions, let's make in red, and the conclusions, let's make in blue. So the conclusion is going to be r has a square root. The assumptions we'll make in red. The first one we have let. R is a positive real number. That's going to be our first assumption. Then it says, write f of x equals x squared minus r for any real x. So that shows that f is a continuous function on r. So our next one is going to be that f of x is x squared minus r is a continuous function on r. And then let's see here, we have if x equals 0, then f of x equals 0 minus r less than 0, since r is positive. Now r is positive is an assumption, but that's an assumption we count for up here, right? And x equals 0 is not really an assumption because we're not really assuming that's true. We're saying if it were true, then this would be the case. And why is it the case? Because we assume that r is positive. If x is very large, then f of x equals x squared minus r is greater than 0. Again, that's the same thing we did with x equals 0 here. We're not saying x is very large. We're saying that if it is the case, then this is the case, right? So by the intermediate value theorem, now this is something we have not proved. This is something we're assuming. Intermediate value theorem, there must be some x such that f of x equals 0. So that is something, using this assumption, we got this. So that's not something we're assuming. For this value x, we have r equals r plus 0 equals r plus f of x equals r plus x squared minus r equals x squared. Now, looking at that, this is actually the conclusion. We said r has a square root is our conclusion. And here we have r equals x squared, right? That's what we wanted to get to here. So I guess this is like the last step on the way to showing that r has a square root. So there's our conclusion right there. R has a square root. Next problem, 2.1.2. A first-year calculus textbook contains the following paragraph, and actually the instructions are down here. What is the conclusion of this argument? Again, we'll do the conclusion in the blue. And what are the assumptions? And the assumptions we will do in red once again. It says here, since it says, look here, you can answer this question without knowing what all the expressions in it mean, I'm going to assume that you don't know what they mean. So I'm just going to show you, just based on the clue words, how you can tell what it is. It says, given that. Now that tells me something like assume that, right? So this is going to be my first assumption. Assume that this. We calculate the limit from, I'm not supposed to say what these mean. So we calculate something, right? Now we haven't calculated it yet. We're just saying we're going to calculate that. Since, so that means assume, right? This and this. The sandwich theorem, something that we haven't proven yet, implies, now so this, and this imply this guy right here, what we were calculating right here, right? So I'm going to line that in blue. That is my conclusion. All right. Next, from your understanding of mathematical arguments, which, if any of the following possible sequent rules seem to be true, give reasons. The first one, sequent rule A. If the sequent gamma entails psi is a correct sequent, and every statement in gamma is also in delta, then the sequent delta entails psi is also correct. I am going to say that that is a correct, or let's say, I'm sorry, that is a true rule. And the reason I'm going to say that is because what it means to be a correct sequent is for all the undischarged assumptions necessary for psi to be in gamma, right? So gamma has all the undischarged assumptions it needs to entail psi. So if it has all those entire undischarged assumptions, and delta also has everything that's in there, which includes all the undischarged assumptions needed for psi, then delta also has all the undischarged assumptions needed for psi, right? So delta also would entail psi. You may be concerned, what if delta has some extra stuff in gamma that we don't really want? Because remember, these are sets. Delta and gamma are sets. So you may think, well, what if gamma doesn't have some extra junk and delta does have it? Well, we don't really care if it does. The reason is because what it meant to be a correct sequent, remember, was just that. All the undischarged assumptions necessary for psi are carried over in gamma, in this thing to the left, right? So everything you need for this is given right here. It doesn't. I don't care if there's extra stuff in there. All I care about is that we have what we need. And delta says we have exactly that. We have gamma and maybe more, maybe not more. So we have at least gamma, so then we are going to get psi. So that is a true rule. Possible sequent rule B: if the sequent, the singleton set phi entails psi is correct, then so is the sequent singleton set psi entails phi. That is not a true rule, and it's not true because just because one statement entails another doesn't mean that second statement entails the first. Here's what I mean. If I have, let's say, let me get my oops, yeah, there it is. Get this guy out here. Let's say phi is the statement x equals 2, right? X equals 2 entails that x is greater than 0. Oh wow, sorry, motorcycle drove by. I'm in my high-tech studio, which is my kitchen, so you're gonna hear all kinds of fun stuff. Yeah, so the singleton set right here, phi, entails psi, right? X equals 2 entails x is greater than 0, but x is greater than 0 does not entail that x equals 2, right? Because just because x equals 0, x is greater than 0, x could be 1, x could be 5, x could be 2, it could be all kinds of different things. So it does not entail psi. So we're going to say that this is not a good rule. No. C. If the sequence gamma entails psi and delta entails psi are both correct, then so is the sequent gamma. The intersection of the sets gamma and delta entails psi. That's correct too. Well, the intersection of two sets means all the things that they hold in common. So, could it be the case that all the stuff in gamma entails psi, and all the stuff in delta entails psi, but the things that they have in common don't entail psi? Well, yeah, I think it could. Here's why. Let's say gamma is the set of statements. I don't know. Let's say x is greater than 0, right? X is greater than 0 entails psi. Let's say psi is x does not equal -1. All right, and then we can give you delta is the set of statements x is greater than 1. Now, x is greater than 1 also entails x equals x. Oh shoot, I'm sorry. X does not equal -1. This is wrong. Yeah, x does not equal -1. So this entails that. Yeah, and this entails that. But these two sets don't hold anything in common. So since they don't hold anything in common, their intersection is actually the null set. There's nothing in there, right? And the null set does not entail that. It does not entail psi. So this rule is not a good rule. Oh, and by the way, you may wonder, why do they have these little guys on the outside up here on this rule? I'm sorry. First, let's do this. You may wonder, why do they have these little guys right here? Because remember, over here is supposed to be a set of statements, and the set can be more than one statement, just one statement, or no statements. And this problem or this rule wanted to show you that we're talking about just one statement, but it's got to be in the set. That's why that thing is right there. All right, well, that's it.